The curse of dimensionality. In machine learning, as you get better and better, and let's say you start solving very complex problems, the greatest problem that you will face is how can you deal with higher dimensions. That is, if let's say you have some input parameter called x, let's say there are multiple parameters x1, x2, x3, x4, and so on, and let's say x1 can take values in the range 0 to 10, x2 can take in 0 to 10, and so on. In this case, considering each of these as different dimensions, you will be dealing with data in higher and higher dimensions as you get more and more input parameters. And let us say in order to solve some particular machine learning problem, you had to consider a lot of parameters and you are dealing with very, very high dimensional data. And here comes the greatest problem computationally and also data wise. That is, as you deal with higher dimensions, you will need much larger data in order to make your machine learn, because it should learn about the characteristics in such a high dimensional space. So there are two problems. One is how you deal with the complexity of this, and secondly, how much data that you have. This problem you're going to face. I'll explain this problem with a very simple example so that you understand it very clearly. Let us say you are doing a classification problem. You'll be given one point in space and you want to identify whether it belongs to the red class or the blue class. This is your problem. In this case, let us say the idea that you use in order to do this classification is like this. You will identify the close proximity space of this particular point. Then you will see inside this box is, let's say, the area in which this point is contained. Then you will see inside this box in which the point is contained, how many of the other data points that are provided are red and how many of the data points that are provided are blue. Depending on this, what you will do, if the red are higher, then you will call this as red class. That is, this particular new data point as red class. If blue is higher, you will call it as blue class. Let us say you are using this simple logic in order to classify this point. If it is one dimensional, what happens? If it is one dimensional, let's say it's like this. And for the easiness, let us say we'll say it can only take, x can only take values up to 4. So 1, 2, 3, 4. X can only take 4 values. 1, 2, 3, and 4. And let's say now you divided data in your space into, one is this area, this area, this area, this area. So you totally have only 4 areas now. Depending, let's say you have some 400 data points. So on average, let's say you'll have around 100 data points in each of these boxes. From this, you can easily identify, let's say I gave a point here. You have to check out of the 100 data points that are present in this box. If 70 are, let's say, red, then you will see this point is also in red class. Simple. What if dimensionality increases? What if instead of 4, instead of one dimension, I have 2 dimension, x1 and x2. Then like this, I have to make each of the point. It will have x1 and x2 coordinates. So let us mark it in the y-axis, 1, 2, 3, and let's say 4. So I'm marking 1, 2, 3, and 4. This time what happened? The number of boxes increased, right? Number of boxes increased by how much? It got squared. Previously it was 4. Now you have 16 different boxes. And initially I had told you have a total of 400 data points. And initially you had 100 data points in each class on average. What happens now? This time you have 16 different boxes. That is 4 square different boxes now. And this time the number of points in each box decreased. Let us go to even higher dimension. Let us say there are 3 parameters, x1, x2, and x3. This time there are total of 4 cube, that is equal to 64 boxes, right? Now this z axis would also come in. There will be more boxes in z axis as well. So considering all this, there will be 64 boxes. What is the next step? Next step is 4 power 4. It will be 256 boxes. If there is one more dimension that comes in, 4 power 5, then it will become 1024 boxes. If it becomes 1024 boxes, then just imagine, even if it is Even in case of 256 boxes, you have a total of 400 data points, which means there is 1 or 2 points in each box if it is distributed very balanced manner, right? If it is 1024 boxes, then you have a total of 400 data points. That means there will be many boxes inside which there will be no point at all, because there are 1024 boxes and only 400 data points, right? So if you get a point inside this box, you won't be able to classify, because this time inside this box you don't have any red point or any blue point. So how will you say this belongs to red or blue? This is the curse of dimensionality. That is, as dimensionality increases, the requirement of data increases exponentially. That is as per the power law. What is power law? Power law says one quantity varies as a power of another. Here what happens? The requirement of data is varying as power of what? Dimensionality, right? As a power of dimensionality, the requirement of data is varying, which means as you go into, let's say, 100 dimensions, 150 dimensions, it will be kind of impossible for you to get that much of data for solving each of the problem. So this is the greatest problem that you have to tackle while dealing with machine learning, especially high-end problems. And this is a classification problem. What if it is a regression problem? Let's say you want to find some y on the basis of some x, let's say like w0 plus w1x, something like this. Like this, you want to find y. Let us say you have only 3 input variables, x1, x2 and x3. In this case, how will your y be defined? Your y will be something like this: w0 plus w1 x1. I'll take only single terms now, that is w2 x2 plus w3 x3, right? Plus, what are the other terms? w12 x1 x2, this is also a term, right? Plus w13 x1 x3, that is combination of x1 and x3. Similarly, there will be w23 x2 x3, this term is also present. Then there will be w123 x1 x2 x3. So all these terms are present in case of simply 3 particular input variables. If it was one variable, only one x1, then only this much is the equation, w0 plus w1x. When it is 3, it became this large. And what is the problem with this largeness? Each of this coefficient you have to identify in your machine learning problem. That is, you want enough data in order to identify all these coefficients independently. So here 1, 2, 3, 4, 5, 6, 7, 8 coefficients are to be found. So in order to identify 8 coefficients, you will need that much of data as well, right? So if your dimensionality increases even further, there will be lots and lots of coefficients. For example, development of ChatGPT, the latest one, they took billions of parameters are there. So that much of data would be required. Just imagine the amount of data that is required in order to train billions of parameters. So this is the problem. You understood the problem, right? So how to deal with this? That's what we are discussing here. So in the future lectures, we'll be looking into different methods of dealing with it. In this lecture, what we'll do, we'll define the base on which those methods are all defined. That is, based on these ideas, those methods will be developed. So here we want to give you an idea of what is the basic concept over which those methods of dealing with higher dimensionality are derived from. Okay. So to deal with dimensionality, there are 2 things you have to take into consideration. What is the first thing? That is, if you take any real data, it will have one speciality. That is, it will often be confined to a small region of the total space, which is having lower effective dimension. That is, even if you have, let's say, even in 2 dimensions, if you consider, you have all the space, right? But in reality, if you take your real data, it will be confined to some space like this. So even though you have all the space, only this much of space which actually has the data, that is only actually required here. This is the only area which is having any sort, which is adding any sort of value to your problem. The remaining area that is there, but it's not actually the area where your data is concentrated. So in terms of any of the real data, you would know that even if your data is of very high dimension, let's say you actually it is of 1000 dimension, in reality your real data will be confined to, let's say, some 50 dimensions. So once you identify these major 50 dimensions on which your data is majorly dependent, you can reduce drastically the amount of running time as well as the data required. You can reduce this drastically if you can identify the most crucial 50 dimensions out of the total 1000 dimensions that is there in your data. So this is the first approach. First concept is that in real data always, even if it is of very high dimensionality, only some of the dimensions will be of value. It will only add value to your final finding from the machine learning problem. So identifying those important dimensions, that is important task. If you identify the important dimensions, you can drastically reduce the dimensionality of your data. So this is the first idea. And what is the second idea? Second idea in dealing with dimensionality is that if you have any real data, it will show some sort of a smoothness. And what is smoothness? Because of the smoothness properties, if you identify some local pattern, you identified some local pattern in your data, this local pattern can be extrapolated in order to make it apply for even higher ranges. So interpolation by exploiting this local data, this is one another technique which you can use in order to deal with higher dimension. That is, instead of actually solving it for all the dimensions, identify the local patterns and try if this can be interpolated in order to accommodate whatever is there in the higher dimensions. So these two particular concepts, these are the base that will help you in dealing with higher dimensionality. The first one is the understanding that real data is actually confined to a lower dimensional space, even if it is present in very high dimensions. And secondly, the local patterns can be interpolated in order to find some sort of patterns in the higher dimensions.